All right, my friends. So 4 combination 2, according to the formula, would be 4 factorial over 4 minus 2 factorial times 2 factorial, which is equal to 4 factorial over 2 factorial times 2 factorial. The 4 and one of those 2 factorials could cancel. You'd be left with 4 times 3, and then you'd still have one of the 2 factorials left over. And there you go. You got 6. So, which is good because that's what we were hoping it would be, right? Now 4 combination 4. So that would be 4 factorial over 4 minus 4 factorial times 4 factorial, which would be 4 factorial over. And I wanted to talk with you about 0 factorial. Just a quick reminder, by definition, 0 factorial is equal to 1. And so you would actually get a 1 here. So note 0 factorial is equal to 1. We mentioned that before, but you could have forgotten pretty easy. So there's a little reminder for you. Anyway, and we're getting, the one that we thought. Now you might be wondering, like, what on earth? You had me start with all these weird lists of A, B, C, D, and then we talked to this combination formula. Where are we going with this? And so here's where we're going with this. Pascal's triangle could be defined in a number of ways. It could be defined in the way that I presented it in the previous lesson, and I'm going to show that. But when I show it, I'm going to make the triangle fairly widespread because we're going to come back and redefine it. So, the 0 power row just had a 1 in it, right? And then the first degree row had a 1 and a 1. Second degree row, coefficients of the third degree expansion, coefficients of fourth degree expansion, etc., right? Notice how wide set I'm drawing this. You might want to follow suit with what you're writing down. Now, if you look back at our first warm-up, I was hoping that you noticed that 1, 4, 6, 4, 1, up here, 1, 4, 6, 4, 1, from Pascal's triangle. So it turns out you can redefine Pascal's triangle in terms of appropriate combinations. And that's what we're about to do. So we're going to take 1, 4, 6, 4, 1, and we're going to replace, for example, that first 1 with 4 combination 0. And that 4 right there with 4 combination 1. The 6 with 4 combination 2, 4 combination 3, and 4 combination 4. There we go. And you could do this to any row in Pascal's triangle that you want. And if you're like me, when you see me do this, you're probably having a little bit of an emotional reaction, like, no, why would you do that? Pascal's triangle was fine. Why would we take a 4 out and put 4 combination 1 in for it? Why would we do that? Well, the answer is this. Even Pascal's triangle can become really laborious and hard to keep the details right if you're raising a binomial to too high of a power. And it turns out that the binomial theorem using combinations can actually keep us out of trouble and can make the calculations, believe it or not, simpler than Pascal's triangle even would have been. And I wouldn't say that that's true for the powers like 4, 5, and 6, like we've done in the previous video. Those we were probably better off with just doing it the way we did it before with normal Pascal's triangle. But if you start having exponents like 14 or 21 or something like that, then this starts being a little bit of a better idea, believe it or not. So anyway, so let's redefine the third degree row. So guess what 1, 3, 3, 1 could be replaced with? Yep, 3 combination 0. That 3 combination 1. That 3 combination 2. And that 1, 3 combination 3. Yep. And you could do this with any row, right? 1, 2, 2, 1. 2 combination 0. 2 combination 1, and 2 combination 2. There you go. The 1, 1, just to be thorough, right? 1 combination 0 and 1 combination 1. And the 1 on the top is 0 combination 1. Strange but true. So the bottom row that I have here would have been 1, 4, 6, 4, 1. And then what would the next row have been? That would have been 1, 5, 10, 10, 5, 1, I think. Yeah. And so that in terms of combinations would have been, whoops, not 4. 5 combination 0, 5 combination 1, 5 combination 2, 5 combination 3, 5 combination 4, and 5 combination 5. Crazy. All right. So now that we've screwed up Pascal's triangle, let's practice kind of moving forward and trying to show how you could use combinations in a couple little moments where it might be a good idea. Let's see. Let's go to example 1 here. Okay. So for example 1, let's see. I think I'll probably start this one with you and have you finish it on your own. The directions are for you to write x plus y to the 7th in terms of combinations. Okay. So this is very much an exercise, just trying to kind of get you to the point where you're ready to do harder stuff. But so x plus y to the 7th. We could use Pascal's triangle to get the coefficients. It wouldn't even be hard. But instead of writing the coefficients down, let's write what combination you could use. So if we were to expand this out, the first coefficient that we get would be from 7 combination 0. And nobody's asking me to evaluate it. They're actually asking me to write this in terms of combinations. So they want me to write 7 combination 0 instead of the 1 that it really would have been, right? That we all know it would have been. And then you'd multiply that by x to the 7th and then times 7 to the 0. And I guess I don't really have to write that 7 to the 0, but I think I will. And then what would the next coefficient be? It would come from 7 combination, 1, x to the 6th, and then times 7 to the 1st. All right, I'll do one more with you, and then I'm going to butt out and let you finish it on your own. So the next coefficient would be 7 combination 2, and then times x to the 5th, and then times your second term there to the 2nd. All right, my friends, I'm going to ask you to finish this out and then check in with me in the next video.